So hi everyone, I welcome you all to this lecture on thermodynamics. So we are in a moving forward in a lecture series of thermodynamics for class 12th physics. So today what we will be going to discuss. So in the previous class we have discussed about work, about first law of thermodynamics. We have discussed law of equipartition of energy. We have discussed different forms of energy. So all of that has been discussed, and in just previous lecture we have did some numericals on work. So today we'll start with uh, first thing, that is proof of Mayer's relationship, and in other half we will be going to calculate work done in different processes. Okay, when I am saying different processes, that means we will be going to calculate work done for isothermal process, adiabatic process, isochoric, and isobaric process. So all of these are the different processes that we have already discussed, and we will be going to derive the formula for work in all of these processes. So let's begin with the proof of Mayer's relationship. So Mayer's relationship is we have already discussed, that is Cp minus, and the name I have not taken previously, but that is Cp minus Cv is equals to R. So that is the relation that we need to derive. So the question is from where it is actually coming and how to relate. Basically, when you look at this relation, you will understand the fact that this is the relationship between the specific heat at constant pressure and constant volume. So basically, we are relating two processes through Mayer relationship, that is at constant pressure, that is isobaric process, and it is isochoric process. Okay. So first look at the isochoric process. So isochoric process means the piston is fixed because we want a constant volume. So let's say we are having this let's say some gas molecules inside the in the piston cylinder system, and this piston is fixed. That means it is at constant volume. Now you are giving an external heat to the system. Let's say Q heat is given. I can make it in yellow color so you will feel it. So some heat is given, that is Q. So Q is given to the system. So we wanted to find out that what is happening with that. So Q at constant volume is nothing but N Cv into dt, right? So this is specific heat at constant volume and this is dt. Now work done, and we need to apply first law of thermodynamics. So I am talking about this isochoric Okay, so applying first law, we know that delta U is Q minus W. So when the volume is constant, we know that work done is always 0, and hence whatever the heat is supplied to the system is going to increase the internal energy of the system. So I hope it is very clear till now that what in isochoric process, whatever the heat you are giving to the system is going to increase the internal energy of the system. So delta U is Cv dt, and I am now taking N to be 1, so that is 1 mole of gas. So this relation I am taking is for 1 mole. Okay, 1 mole of gas is there. Now, so this is everything about isochoric process. Now let's look at what is happening to isobaric process, if the same thing is happening to the isobaric process. So in case of isobaric process, we are having a again cylinder piston system where the gas molecules are present inside the inside the cylinder, and now in this case this piston is movable. So basically we are moving the piston, so the piston is movable. It means to say that we need to make the volume, we need to make the pressure constant, and the only way to do is to change the volume, and so that is there. Okay, so again we are giving heat to it, some heat Q is given to the system, and so Q is given to the system. Now Q is, I am again considering 1 mole of gas, so Q is nothing but Cp dt, and work done is integration of P dV. So P is constant and whatever the volume we have changed, it is there. Okay, so can I so now when I am applying first law of thermodynamics, I always used to write delta U is equals to Q minus W. So can I write it to be like this, du is equals to dq minus dw. So whatever the change in internal energy should be equals to the change in the amount of heat given to the system minus the work done by the system. So so usually when so first law of thermodynamics is written in this way, and so delta U is there, and so from here we can understand that dq, so du is nothing but Cp dt, that is coming from the previous we have defined from the isochoric process. Okay, dq here is Cp dt. So this is Cv dt actually. So I already reiterate that always remember the change in internal energy is Cv dt, and dw is P dV. Okay, so this is coming from here, this is coming from isobaric process, and this is also coming from here. So dw is P dV, that is simple. So just put all these things here. So du is Cv dt dq is Cp dt minus P dV. So Cp, can I rewrite it Cp minus Cv into dt is equals to P dV, and Cp minus Cv is nothing but P dV by dt. From ideal gas law, PV is equals to RT, and at constant pressure, because this isobaric process we are looking at, so at constant pressure dV by dt is equals to R at constant pressure. So dV by dt is nothing but R by P. So Cp minus Cv is equals to P, sorry, dV, it's dP, dV by dt, dV by dt, and so that is R by P into R by P. So Cp minus Cv is equals to R. So that is for 1 mole of ideal gas. For n moles, it is PV is equals to nRT, and n is coming here, here, here. So n will cancel out, and eventually, so it is valid for any moles of gas. So that has to be clear. Okay, let's recall the different processes in thermodynamics. Okay, so these are adiabatic, which means that delta Q or dQ is 0. Then we have isothermal process, which means that delta T is 0. We have isochoric, where delta V is 0, and we have isobaric, where delta P is 0. So first we'll look at isothermal process. So we need to find out. So our aim is to find out the slope of a PV curve and work done in different processes. Okay, because some questions will come on how the slope is changing for a particular process, and then we need to derive the work done for different processes. So first we will be going to go through the isothermal process. So isothermal process means delta T is 0 or T is constant. So let's say we are having an ideal gas present, so in the last Mayer's relation, just remember one thing, that it is valid for any mole of gas, any mole of an ideal gas. So this is to be keep in mind. So this is for ideal gas. Okay, so we are having an ideal gas, and the process is happening in a way that the net temperature of the gas will remain constant. So we are again supplying heat to this. So heat is supplying to this, and okay, and this is the ideal gas. What we are looking at, we are putting some blocks over here. So in order to have a isothermal process, what we will see is that whatever the heat is going will be converted directly into the work. Why I am saying so? Because the change in internal energy, that is Q minus W. So delta U we know for, that is N CV dt, and we know for isothermal process this is 0. This means that delta U is 0. So Q should be equal to the work done by the system. So whatever the heat is given to the system is going to change the volume of the system, and it is so slow, the process is so slow that temperature will remain constant. So process is slow enough to have constant temperature. So you are giving heat and piston is going up, and so these are the blocks that are so the amount of work done is equal to the weight of this block. Okay, so the process is slow enough so that we are having a constant temperature. So for this case, if I have to look at the ideal gas law, so that is nothing but PV is equals to nRT, and if I wanted to find the slope of PV diagram, so T is constant and R is constant, so P will eventually, so I can call it to be K, so P will come to be K by V. So if I want to find out the slope for this, let's take the partial differential for this PV. So dP into V plus P dV is equals to 0, and dP by dV is nothing but minus P by V. Okay, so from this process you can plot the curve for isothermal process, so that is PV. The slope is negative, and so it will come to be like this. Okay, so dP by dV is nothing but minus P by V. The slope is this at constant temperature. So we'll end this here for now. In the next part we will be going to find out the work done. Thank you.